Good morning, everybody. Today we will discuss about velocity and thermal boundary layers. Now, if we recall, in the last class, we derived the general form of energy equation, which is valid for compressible as well as incompressible flows, that is given by this equation rho Cp dt d time. This is total derivative which has temporal and convective derivatives, and so temporal and convective derivatives together, total derivative. Again, total derivative of P plus K grad square T or K del square T plus mu into phi. This is viscous dissipation function. Total term is viscous dissipation plus thermal energy generation rate if there is any volumetric heat source present within the body, within the system or within the control volume. Now this is the general form of energy equation. Special case is rho Cp and Cv, same for liquid. So rho C, again total derivative of temperature K, this is grad square T plus mu into phi. This is also viscous dissipation plus thermal energy generation rate. But this viscous dissipation, when it is applicable for incompressible flows, it will differ than the viscous dissipation term with general energy equation, because we will invoke basically the continuity equation here, that is del u del x plus del v del y for 2 dimension equal to 0, 3 dimension del u del x plus del v del y plus del w del z equal to 0. That will be invoked in the expression for viscous dissipation. Now we will try to identify the important dimensionless numbers. So what we do, we go for energy equation, for general energy equation, irrespective of compressible or incompressible flows, and we assume that thermal energy generation rate is 0. And then the velocities are non-dimensionalized with respect to a reference velocity, which is u infinity. If it is flow over a flat plate, for example, when the flow has not come over the flat plate, the approach flow, the u infinity is basically the unperturbed flow. So u star is basically u by u infinity. Similarly, v star is v by u infinity. W star is w by u infinity. We non-dimensionalize theta with respect to free stream temperature. That means, again, the incoming, in case of flow over a flat plate, we can assume the incoming flow, which has no effect of the surface temperature, and TW, which is the temperature of the if it is heated flat plate, temperature of the heated flat plate. So T minus T infinity divided by TW minus T infinity. It is done in such a way that the theta will vary between 0 and 1. Maximum will be 1, T will be equal to TW, then theta will be 1. Minimum will be 0, T will be equal to T infinity. X is non-dimensional x, y, and z. These are non-dimensionalized by the reference length scale, and these are x star, y star, z star. Pressure is non-dimensionalized by rho u infinity square. Time is non-dimensionalized by convective time scale. Now, convective time scale is given by L divided by u infinity. So, this L divided by u infinity, if we divide time by that quantity, then we get T into u infinity by L. So, T star is the non-dimensional time. Time has been non-dimensionalized by convective time scale. Now, in the governing equation, we keep substituting T by theta, U by U star, V by V star, W by W star, X, Y, Z by X star, Y star, Z star, time by T star, pressure by P star, and so on. Then what we do, we try to retain non-dimensional quantities inside the bracket and pull out other terms outside. So, for example, if we do that for the convective terms, outside we will get rho Cp Tw minus T infinity into U infinity by L. Here, if we do that, same thing. Inside we will get all these terms, P star by del P star by del T star, U star, del P star, del X star, etc. And outside we will get rho U infinity cube by L. Similarly, here, if we do the same exercise, we will get basically K Tw minus T infinity divided by L square outside, and inside we will get del 2 theta del x2, del 2 theta del y2, del 2 theta del z2. Similarly, from viscous dissipation, if we do the similar keeping non-dimensional terms together inside the bracket, we will be able to pull out mu u infinity square by L. Then, as I said, that left hand side we will have rho Cp Tw minus T infinity into u infinity divided by L. So that quantity we will remove from left hand side and bring to the right hand side. So that means whatever groups came out of each term, each bracketed group of bracketed terms, those terms will be divided by rho Cp Tw minus T infinity into U infinity by L. So if we do that, then left hand side we will get del theta del T star, U star del theta del X star, V star del theta del Y, W star del theta del Z star equal to, here, this group of terms will create, group of parameters will create U infinity square divided by Cp Tw minus T infinity. And here within the bracketed terms, within the bracket we will get del P star divided by del T star, U star del P star divided by del X star, V star into del P star divided by del Y star, etc. This second term will get K divided by rho Cp U infinity by L outside the bracket. Inside the bracket we will get del 2 theta del X star 2 del 2 theta del y star 2 del 2 theta del z star 2. Similarly, viscous dissipation, you have seen these terms are like del u del x square, del v del y square, etc. So basically from those terms we have pulled out mu u infinity square by L, and within the bracket we will get basically del u star by del x star square plus del v star by del y star square, etc. Just typical viscous dissipation components of viscous dissipation terms, which we have written here as phi bar. And then from left hand side, rho Cp Tw minus T infinity into U infinity by L will come, and here denominator, sorry, if we pull out we will get U mu U infinity square by L square. So that L square into L, which is coming from left hand side, one L will cancel out. So we will get mu U infinity square by L rho Cp Tw minus T infinity into U infinity multiplied by the non-dimensional viscous dissipation function. So this is the non-dimensional form of equation. And now we can identify all these terms which are basically coming out from the bracket. We will be able to form non-dimensional groups. For example, this one is Eckert number, and this group is 1 by Prandtl number into Reynolds number. This group is Eckert number by Reynolds number square. So this term is basically Eckert number by Reynolds number. So we can write here del theta del T star, U star del theta del X star, V star del theta del Y star, W star del theta del Z star equal to Eckert number into, we can see del P star del T star plus U star del P star del X star, etc. Then 1 by Reynolds number into Prandtl number into del 2 theta del X star 2 del 2 theta del Y star 2 del 2 theta del Z star 2 plus Eckert number by Reynolds number into again non-dimensional viscous dissipation function. Now Eckert number we have seen, this is basically U infinity square divided by Cp Tw minus T infinity. Prandtl number is mu Cp by K, and Reynolds number is rho U infinity L by mu. All of you know that these group of numbers are named after very well known scientists, like Reynolds number. It is named after Osborne Reynolds. Prandtl number, it is named after Ludwig Prandtl, and Eckert number, it is named after E.R.G. Eckert. In my introductory lecture, I have mentioned about enormous contribution of these scientists like Reynolds, Prandtl, Eckert. As such, they have basically their findings, their contributions started the fields of modern fluid mechanics and modern heat transfer. Modern in a way I'm saying, because mathematicians have been practicing quite a few of these solutions even from late 1700s. Now in the form of fluid mechanics that we practice today, in the form of heat transfer that we practice today, these are outcome of enormous contribution and efforts from scientists like Reynolds, Prandtl, Eckert, and few others we will mention in course of our discussion. Now let us look at the term Eckert number. Eckert number is given by U infinity square divided by Cp Tw minus T infinity. This is basically physically can be sort of presented as kinetic energy of the flow divided by boundary layer enthalpy difference. We have not precisely defined boundary layer. When we will do that, this is basically enthalpy difference across the boundary layer. Tw if it is the temperature of the heated body, and T infinity if it is the temperature outside the boundary layer, then enthalpy across the boundary layer is basically Cp Tw minus T infinity, enthalpy difference. So we write 1 by Eckert number, Cp Tw minus T infinity by U infinity square. Then we pull out T infinity from inside, Cp T infinity by U infinity square, T infinity, Tw by T infinity minus 1. Now we multiply both numerator and denominator by gamma R. Gamma into R. R is the gas constant. Gamma is the ratio of Cp by Cv. It may be called as polytropic index. So if we multiply both the sides by a gamma R T infinity is basically a square of local acoustic speed. So gamma R T infinity we have written as a square. A square is square of local acoustic velocity into Cp. And here gamma R, all of us know R is Cp minus Cv. So gamma R we have written as, gamma into Cp minus Cv into U infinity square. Bracketed terms remain same. And then if we can do a little algebra, from here Cp divided by gamma, Cp minus Cv, we get 1 by gamma minus 1. And here U infinity square by A square, that means local velocity by local acoustic speed, is Mach number. So it is 1 by Mach number square. And here we get a Tw by T infinity minus 1. So Eckert number is given by gamma minus 1 into Mach number square, Tw by T infinity minus 1. Now what we can estimate, basically for incompressible flows or low subsonic flows, Mach number is 0.3 or below. So this is 0.3 square, that means 0.09, roughly the order, multiplied by gamma minus 1, diatomic gases and air, gamma whatever we take, this is also something like 0.3, 0.4. So again if we multiply, it is 0.0027 or something like that. Now gamma 1.3, 1.4, whatever we take, we get from here 0.3 or 0.4, and we multiply that with 0.09. So in the numerator we get a quantity which is 0.00, then some number starts 002 or so. Now so Eckert number for Mach number less than 0.3 is very low. So we have written that basically for low Mach number situation, energy equation. So since Eckert number is becoming very small, we can ignore this term. Also we can ignore this term. And then we get del T star, U star is del theta del T star plus U star del theta del X plus V star del theta del Y, W star del theta del Z equal to 1 by Reynolds number into Prandtl number, del 2 theta del X star 2 del 2 theta del Y star 2 plus del 2 theta del Z star 2. Now, if we go back two-dimensional form from this governing equation, we can write rho Cp into U del T del X, V del T del Y, W del T del Z equal to K del 2T del X2 plus del 2T del Y2 plus del 2T del Z2. So for forced convection, the variables can be presented as it's like solution of theta, where theta is a function of U, V, X, Y, Reynolds, Prandtl, and T is the temperature. So if we can find out everywhere T or theta, then from there, from wall to fluid heat transfer, we can calculate as QW equal to K minus Kf, and this heat transfer may be considered per unit area. So like heat flux, so minus Kf into del T del eta, and this can also be written if we follow Newton's law of cooling, that convective heat transfer coefficient into del TW minus T infinity. N is the dimension in the direction normal to the solid surface. So from here we can write H equal to, and look at this quantity, this is thermal conductivity, but deliberately we have added F to give emphatic attention to this. This K is K fluid into del T del N TW minus T infinity, or we can write minus Kf if we non-dimensionalize this quantity del T del N, TW minus T infinity by L into del theta del N bar, where N bar is N by L, just N, the normal direction. We are non-dimensionalized with the length scale. So here we can rearrange the terms and we can write H L by K equal to Nusselt number equal to minus del theta del N. And this HL by KF, this is K fluid, is a very important non-dimensional group which is known as Nusselt number, named after again a famous scientist, German scientist, Wilhelm Nusselt, and this is called Nusselt number. Just I would like to remind you that we were introduced to one similar number which was BO number. But in the case of BO number, it was HL by K, but that was K of solid. In case of Nusselt number also, it is HL by K, but here it is K of fluid. So HL by K, when K is thermal conductivity of the fluid, it is Nusselt number. So it is basically heat transfer to the fluid layer, which is immediate adjacent to the solid surface and which is adhering to the solid surface. And that is why to that fluid film we assign this Nusselt number, and H is the film heat transfer coefficient, L is the length scale, K is the thermal conductivity of the fluid. Again, let me mention, when thermal conductivity of solid is considered, then it becomes BO number. Okay, so now Nusselt number is minus del theta by del N bar. Therefore, Nusselt number, which is given by HL by thermal conductivity of fluid, HL by K, that is physically we can get a meaningful expression which is basically non-dimensional temperature gradient at the surface of interest. Now we will go for discussion on boundary layers. Now, transition of zero velocity at the surface to free stream velocity delta takes place through a very thin layer, free stream velocity u infinity. Extremely sorry. Transition of zero velocity at the surface to free stream velocity u infinity through a very thin layer delta. It is basically this takes in case of flow over a solid surface, we can observe that, and this thin layer is basically boundary layer. Let me tell you, this boundary layer was discovered in 1904 by a genius, Professor Ludwig Prandtl. Before that, usually mathematicians used to solve the potential flow equation, which is inviscid irrotational flow, for solving the fluid motion on any geometry of interest. But as I said, it is genius of Professor Prandtl who discovered that there lies a very thin viscous layer immediately on the surface, and fluid velocity, which is zero on the surface, increases slowly to the full scale velocity, which is u infinity, through this thin layer, and this thin layer is called boundary layer. And he devised experiments, very elegant experiments, to prove the existence of boundary layer, and also he developed theory. So both theoretical and experimental development took place under the tutelage of Professor Prandtl, and existence of boundary layer was accepted by all the peers in the field, and it happened in 1904. Now let us come back to our discussion. The quantity delta is termed as boundary layer thickness. From this picture we can see, and it is formally defined as the value of y for which u becomes 99% u infinity. So in the picture, it's a flat plate, approach flow is uniform everywhere u infinity. It is coming on the flat plate. Immediately on the plate at y equal to 0, it is supposed to be 0. And then, viscous resistance will act within the boundary layer, and slowly and steadily from 0 it will reach u infinity velocity, and this thickness of this layer is very, very small, of the order of millimeter, we can say now. Later on we will try to quantify. And then outside the boundary layer, it attains the full scale velocity, which is u infinity. So when it reaches 0.99 u infinity, we can call that value of y from the wall is the boundary layer thickness. Now, clearly this divides the flow field in two different regions. The region where del u del y and consequently shear stress is significant. So here within this we can see del u del y is obvious presence of del u del y because of velocity gradient. Velocity is transiting from 0 to u infinity, or here if it u infinity is varies from location to location, we can say ux. For flat plate it will not vary, but for curved geometry it may vary. The free stream flow, we'll again do elaborate discussion on that. For the time being, let us assume this as u infinity. So the region where del u del y and consequently shear stress is significant, this region. And region where del u del y and shear, clearly outside this, there is no velocity gradient in y direction because everywhere it is u equal to u infinity. So shear stress is also absent. We can say del u del y 0. So within the boundary layer, del u del y is non-zero. Outside the boundary layer, del u del y is 0. Here, del u del y determines the local friction coefficient, and from our fluid mechanics knowledge, we have seen that this growth of delta is proportional to x power half, and we can more formally write it as delta function of x equal to 5 into x. That means the x where we are defining or where we are measuring delta at that x. So delta x, which is function of x. So at a given x, delta x is 5 into x divided by root over rex, where rex is given by u infinity into x by nu. Now Cf is Tw by half rho u infinity square. This is skin friction coefficient, where it is basically non-dimensional shear stress. So what is the value of shear stress? Shear stress is mu into del u del y at y equal to 0. So slope del u del y then plays a very important role. And we can see, since the boundary layer thickness is increasing and velocity is reaching from u to u infinity through the boundary layer, that means through delta, very rudimentary way of describing slope is u infinity minus 0 by delta. Now since delta is increasing, basically the slope will decrease, and here we can see the how the slope changes. Here this is delta, and through this distance velocity is reaching from u to u infinity, and slope is beta 1, and we will get del u del y some value. From there we will be able to calculate shear stress. But at this location, velocity is reaching 0 to u infinity through another length which is bigger than delta 1, delta 2. So slope is changing, and also basically shear stress is changing. So basically this shows that because of change in gradient along the wall, how shear stress may vary, or due to change in boundary layer thickness, how the gradient and shear stress can vary along the length. Now thermal boundary layer, this is almost to say analogous to velocity boundary layer. Just as the velocity boundary layer, a thermal boundary layer should develop if the temperature at the fluid phase stream and the solid surface differ. fluid particles that come into contact with the plate achieve thermal equilibrium of the plate's surface temperature, and the temperature gradient develops in the fluid. So fluid layer which is adhering to the surface, and if the surface temperature is Tw, so fluid layer at a location X, and that fluid layer is having temperature equal to Tw because of thermal equilibrium between the fluid layer, which is at a no slip condition on the solid surface. Solid temperature is Tw. And again, approach flow, its temperature is T infinity. When it comes on it, since T infinity is less than Tw, heat transfer starts taking place, and temperature adjacent to the wall also changes. The region of the fluid in which these temperature gradients exist. So a temperature gradient will be set, but again, if we given X, if we move perpendicular to the plate, and immediate adjacent to the plate it is Tw. If we move perpendicular to the plate, we will see temperature is reducing, and finally it becomes a free stream temperature. So basically the thermal boundary layer is that distance delta T through which fluid temperature reaches free stream temperature from the wall temperature. So value of Y, for which we are saying Tw minus T divided by Tw minus T infinity equal to 0.99. So here it is this T theta is varying, or this T is varying in such a way that at the wall it is Tw, but here it is becoming T infinity. And if it becomes T infinity, then it is 1 Tw minus T infinity divided by Tw minus T infinity. But when it approaches value of T infinity, just onset of touching T infinity, we can call that distance as delta T. So we have given 0.99, just like velocity boundary layer. So any distance that is so this delta T is basically thermal boundary layer thickness. We can clearly see fluid temperature from Tw is reaching T infinity and not changing any further, so through this distance. At any distance from leading edge, then heat flux can be calculated as minus Kf del T del Y at Y equal to 0. Now because at the surface energy transfer is through conduction, the expression is exact because at the surface there is no fluid motion. We apply no slip boundary condition, and we can write H Tw minus T infinity film heat transfer coefficient into Tw minus T infinity equal to minus Kf into del T del Y at Y equal to 0. But this conductivity is the conductivity of the fluid. So H is given by minus K del T del Y at Y equal to 0. K is Kf divided by Tw minus T infinity. Here the conditions in the thermal boundary layer which strongly influence the wall temperature gradient is del T del Y at Y equal to 0 determine the rate of heat transfer across the boundary layer. So obviously this del T del Y, this gradient, that determines finally the heat transfer at the wall, from wall to the fluid. Since Tw minus T infinity is a constant and delta T increases with increasing X, temperature gradient in the boundary layer must decrease with increasing x. Very clear, because from world temperature we will reach T infinity temperature, free stream temperature, through thermal boundary layer. Now thermal boundary layer, if at this x location is given by del T1, it is much, whatever it is, if we can measure that, and if we walk along the surface in the downstream, thermal boundary layer thickness increases, and at this x, it is delta T2 is the distance we need to cover to reach the temperature T infinity. Exactly, that is what has been written here, that temperature gradient in the boundary layer must decrease with increasing x, because delta T is increasing. So temperature gradient must decrease. This means del T del y at y equal to 0 decreases with increase in x, where heat flux and h also decrease with increase in x. Because del T del y, we explained it, thermal boundary layer thickness is increasing in the x direction, which is why the temperature gradient, because gradient is given by Tw minus T infinity divided by delta T. So delta T is increasing, gradient is decreasing, and since gradient is decreasing, H will also decrease, and we will see that heat flux will also decrease in the flow direction. So this means del T del y at y equal to 0 decreases with increase in x, whereby heat flux and h also decrease with the increase in x. Now we will very briefly try to derive the boundary layer equation, governing equations for the boundary layers. So in 2D, if we write the full Navier-Stokes equations for incompressible flow, we can write del u del T plus u del u del x plus v del u del y equal to minus rho del P del x plus nu del 2u del x2 plus del 2u del y2. Del v del T plus u del v del x plus v del v del y minus 1 by rho del P del y plus nu del 2v del x2 plus del 2v del y2. These are x momentum and y momentum equation, and del u del x plus del v del y equal to 0 continuity equation. In the region very near to the wall, fluid motion is retarded until it adheres to the surface. The transition of mainstream velocity from 0 at the surface to full magnitude takes place through the boundary layer. The thickness is delta, which is function of x. In order to find out velocity distribution in the field and velocity gradients at the wall, full Navier-Stokes equations should be solved. This is almost impossible analytically and can be solved only by numerical techniques. So easier approach would be to divide the flow field in two regions, inviscid and viscous region. The inviscid flow is irrotational in this case, and we solve different governing equations in the inviscid zone and the boundary layer zone. And inviscid zone, it is basically potential flow equations, but in the boundary layer we solve the boundary layer equations. To solve the governing equation in the boundary layer zone, boundary layer equations are to be derived. So here we make an attempt to derive the boundary layer equation from order of magnitude analysis. What we do, the dimensionless variables, again we non-dimensionalize u by reference velocity u infinity, v by reference velocity, again u infinity, u star v star, p star by reference dynamic pressure head rho u infinity square, x star is x by L, y star is y by L. So this equation becomes u star del x star plus v star del u star del y star equal to minus del p star del x star, plus here obviously we get 1 by Reynolds number into del 2 u star del x star 2 plus del 2 u star del y star 2. Similarly, we get V momentum equation, and V momentum equation pressure gradient is minus del P star del Y star, and also in the viscous term we get 1 by Reynolds number into del 2 V star del X star 2 plus del 2 V star del Y star 2, and this is the inertia term. And this is the continuity equation, del u star by del x star plus del v star by del y star equal to 0. Now u, let us define the scales. Following are the scales for the boundary layer variables. Variable u can go maximum up to u infinity. So with respect to u infinity, if we non-dimensionalize, the non-dimensional scale, its maximum value is 1. Similarly, x, the flow direction, if the L is the plate length, flow over a flat plate, so at the end of the plate, all these dimensions, x star is supposed to be 1. Y is meaningful up to a very small length and or a very small length scale, it is delta. Beyond delta, if we progress along y direction, it doesn't carry any sense because velocity doesn't vary anymore. So y is its dimensional scale, dimension of y till delta is non-trivial. Beyond delta, it becomes trivial. And this delta is given by delta, if we non-dimensionalize it with respect to L, we can call this as epsilon. And obviously, epsilon, our basic assumption of Professor Prandtl was this viscous layer is very, very small. So how small? Epsilon is much, much less than 1. So consider the continuity equation. Now in the continuity equation, we can see this is then of the order of 1. Del u star by del x star. This is of the order of 1. This is of the order of 1. But continuity equation is mass conservation equation. Neither can we create mass, nor we can destroy mass. Neither mass can be created nor can it be destroyed. So del v star del y star cannot be dropped. This has to have same order of del u star del x star. This should be order of 1. So, but here we can see y star has a scale which is of the order of epsilon. That means v star should, in order to have order 1 of this term, v star should also be order of epsilon. Then only del v star by del y star will be of the order of 1. So from here we get the order of v star. And then we substitute U star order of 1, del U star del X star 1 by 1, V star order of epsilon, del U star del Y star, del U star of order of 1, Y star order of epsilon, and V star order of epsilon. Del P star del X star will now not talk about it. 1 by Reynolds number will not talk about it. We will come here. Here we can see this will be of the order of 1 by 1, and this will be order of 1 by epsilon square. Similarly, Y momentum equation, we can write 1 epsilon by 1, V star is order of epsilon. Again, V star order of epsilon, V star order of epsilon, Y star order of epsilon. Del P del Y we'll discuss little later. 1 by Reynolds number we'll discuss little later. But here it is epsilon by 1, and this is epsilon by epsilon square. And continuity equation, del U star del X star is 1 by 1, del V star del Y star is epsilon by epsilon. So first let us work on order of 1 by Reynolds number. There we can see existence of boundary layer is appreciated when Reynolds number is very high. Now, in terms of Reynolds number, what is the order of magnitude of the boundary layer? Now, high Reynolds number flow means Reynolds number is ratio of inertia force by viscous force. It is inertia force is much higher than viscous force. But within the boundary layer, the order of viscous force and inertia force are same. So within the boundary layer, the inertia term we can write as rho U del U del X. Order of U is U infinity. Del U del X is U infinity by L into rho. So this is inertia force. And viscous force is mu del 2U del Y2. So basically U infinity by delta square. And from there we can write rho U infinity into L by mu equal to L square by delta square. Then Reynolds number becomes 1 by epsilon square. So when we get Reynolds number as 1 by epsilon square, here we substitute this 1 by Reynolds number is epsilon square, because Reynolds number is 1 by epsilon square. So 1 by Reynolds number is epsilon square. 1 by Reynolds number is epsilon square. And then this equation is balanced with order 1 on both the sides, and pressure gradient is commensurate with that order. So del P del X is also of the order of 1. So X momentum equation has order 1. Y momentum equation, 1 by Reynolds number, if this becomes epsilon square, then we have to see what is basically emerging from here. We'll assign that to del P del Y. So let us move, and then here if we retain terms of order 1, this is order 1, we can see 1, 1, 1 will be retained. This term is of order 1, epsilon 1 by epsilon will retain. This is of the order 1. And here, since Reynolds number is of the order of epsilon square, in the bracketed terms, this is 1 by 1, and this term is 1 by epsilon square. So when we multiply, first term becomes epsilon square, much smaller than 1, can be dropped. Second term is of the, after multiplication, its order is 1. So we'll retain that. That is why the equation, which is consistently of order 1, we can write U star del U star del X star plus V star del U star del Y star equal to minus del P star del X star plus 1 by Reynolds number del 2 U star del Y star 2. And del P star del Y star, now we will see here, order of this term is epsilon. Order of this term is epsilon. Now after multiplying with Reynolds number, since Reynolds number is order of epsilon square, within the bracket earlier we got this is epsilon by 1 and this is epsilon by epsilon square. So after multiplication, these terms become epsilon cube and this term becomes epsilon. So highest term, highest order of this equation is epsilon. So from here we can write del P star by del Y star is order of epsilon. Now meaning of this is the following. There is no variation in pressure in Y direction within the boundary layer. Pressure is impressed on the boundary layer by the outer flow. The pressure P is only function of X within the boundary layer. So within the boundary layer, pressure is a function of X, but pressure is not a function of Y. In Y direction, at any X location, whatever is the pressure outside the boundary layer, that is the pressure on the solid surface. Another X, whatever is the pressure outside the boundary layer, that is the pressure on the solid surface. So pressure on the solid surface will be determined by pressure distribution in the X direction outside the boundary layer. Across the boundary layer at a given X location, pressure will not change at any Y within the boundary layer at a given X. So del P star del Y star is order of epsilon, or we can say del P del Y is order of very small quantity, order of can be neglected. At the outer edge, the boundary layer, outer edge of the boundary layer, if we substitute X momentum equation, so this X momentum equation, if we extend it outside the boundary layer V star is 0. So from left hand side we will get U star del X star. And right hand side again this velocity gradient and is further derivative, which is curvature term basically, but U star will not change in Y outside the boundary layer. So this term will be dropped. We can write minus del P star del X star. In dimensional form we can write U del X equal to minus 1 by rho del P del X. If we integrate it, we will get P plus half rho U square equal to constant. What is this? This is Bernoulli's equation, which is valid outside the boundary layer between any 2 points. Now, if it is inviscid irrotational flow, obviously between any 2 points. Boundary conditions: Y equal to 0, U equal to 0, V equal to 0, or at Y star equal to 0, U star equal to 0, V star equal to 0. At Y equal to delta, U is U infinity. In terms of non-dimensional variable, at Y star equal to epsilon, U star equal to 1. Outside the boundary layer, U star equal to 1. Non-dimensional velocity. Now, from here, we can attempt to derive thermal boundary layer equation. In order to derive thermal boundary layer equation, we have to first take help from definition of Prandtl number. Prandtl number is given by mu Cp by K. We can rearrange it as mu by rho into rho Cp by K or mu by alpha. That means kinematic viscosity divided by thermal diffusivity. And this is of the order of velocity boundary layer thickness by thermal boundary layer thickness. So, energy equation, when we non-dimensionalize, we have already seen it and we have worked with it, non-dimensional parameters. So, for 2D, now we can write U star del theta del x star plus V star del theta del y star equal to 1 by Reynolds number into Prandtl number del 2 theta del x star 2 plus del 2 theta del y star 2. And order of magnitude analysis, U star is of the order of 1, theta of the order of 1. We have seen maximum value of theta can be 1, minimum can be 0. X star order of 1, V star order of epsilon, del theta order of 1, del y star order of epsilon. And del theta del x2 again 1 by 1, del theta del y2 1 by epsilon square. And here this order we have to assign. We have retained the order of Reynolds number. Usually the Prandtl number for all working fluids, it is such that it doesn't change this order of magnitude value of 1 by Reynolds number. Why I am saying so? That Prandtl number varies in a wide range 0.01 liquid metals to a value 1000. Now, for higher value of Prandtl number, this order will not change. For value of Prandtl number of the order Prandtl number in the range of 1, 0.6, 0.7, 5, 6, 7, 10, basically, 1 and greater than 1 is not a problem. Less than 1 is a problem, but less than 1 usually for most of the gases the value is like air, it is around 0.6. Now, so basic or 0.72, very precisely. It ranges from basically, 0.6 to 0.72, 73, something like that, depending on temperature. Usually value is, what is used is 0.7 and 0.6 is not correct, 0.7. So for all those values will not change 1 by Reynolds number order. What will change is very small value, which are the values of basically Prandtl number of liquid metals. Now we can sort of, exclude liquid metal from our analysis. So for all other fluids, we can say that 1 by Reynolds number into Prandtl number is of the order of epsilon square. Then again, if we want to retain order of 1 on both the sides, we'll be able to write U star del theta del x star plus V star del theta del y star equal to 1 by Reynolds number into Prandtl number del 2 theta del y star 2. Non-dimensional value. Dimensional value, if we go back from here, we will get rho Cp U del T del x V del T del y equal to K del 2T del y2. Physical significance is basically del T del x is not to be dropped as it is 0 on that argument. it's to be dropped because del T del Y is much greater than del T del X. That is, axial conduction in fluids is much less than that of the diffusion rate. That means the cross diffusion in the normal direction. So axial conduction in fluids much less than that of the transport or diffusion rate in the normal direction. Please note that del T del X cannot be 0 because if the heat transfer is taking place, del T del X will change as long as heat transfer is taking place. However, del T del Y is much greater than del T del X. So, Nusselt number, we can say that dimensionless temperature gradient at the surface, it becomes a function of U star, V star, X star, Y star, theta, Reynolds number and Prandtl number for forced convection in the absence of dissipation and volumetric heat generation. This can also be shown that non-dimensional form of thermal boundary layer equation becomes U star del theta del X star plus V star del theta del Y star equal to 1 by Reynolds number into Prandtl number del 2 theta del Y star 2 plus Eckert number by Reynolds number into 2 into del U star del Y star square. This is the highest term in the viscous dissipation function, del U del Y gradient if it is significant. So we have in the entire viscous dissipation function, we have only retained this term. This is in presence of viscous dissipation and subsequent. So this is the equation. As we said, this can be shown that the non-dimensional form of thermal boundary layer equation becomes this in the presence of viscous dissipation, and its dimensional form then rho Cp U del T del X plus V del T del Y equal to K del 2T del Y2 plus mu twice del U del Y square. Just its analogous dimensional form. So in the above analysis, del U del Y square has been considered as the leading representative term of the viscous dissipation function. I have already explained it. So in such a case, the Nusselt number becomes function of U star, V star, X star, Y star, theta, Reynolds number, Prandtl number and Eckert number. So in absence of viscous dissipation, Nusselt number, when we will determine, it will be function of U star, V star, X star, Y star, theta, Reynolds number and Prandtl number. And in presence of viscous dissipation, it will be function of U star, V star, X star, Y star, theta, Reynolds number, Prandtl number and Eckert number. Now quickly I will give a few definitions which already you know, but we will just recapitulate it. Boundary layer thickness, we know over a flat plate at any x is given by delta equal to 5x divided by root over Reynolds number based on x. That means U infinity into x by nu is the Rex. So root over Rex. Now displacement thickness is basically distance by which the external potential flow is displaced outwards as a consequence of decrease in velocity in boundary layer. So you can see that within the boundary layer, velocity increases from 0 slowly to the full scale velocity or the free stream velocity, which is attained at the edge of boundary layer. So there is basically, as if some fluid mass is not allowed to flow through due to viscous resistance. So this is, had there been a potential flow throughout, so how much is external potential flow would have been displaced as a consequence of decrease in velocity in the boundary layer. So that we can estimate if u is the free stream velocity outside the boundary layer, uppercase U. So uppercase U into delta star, this is 0 to infinity integration of u minus u infinity, that is the discrepancy. So from uppercase U minus lowercase u. So uppercase U minus lowercase u, this is integrated between 0 and infinity, and this integration is equivalent to u delta star. So delta star, this thickness, displacement thickness, is given by integration 0 to infinity 1 minus lowercase u by uppercase u dy. So this is the definition of displacement thickness. In the similar way, momentum thickness delta double star is defined as the loss of momentum in the boundary layer as compared with that of potential flow. So here simply we, when calculating displacement thickness, we calculated that the volume or mass by which the potential flow is as if displaced, because as a consequence of decrease in velocity in the boundary layer. Here, as a consequence of decrease in velocity in the boundary layer, what is the basically momentum that is lost in the boundary layer, or rather momentum thickness, we can say that loss of momentum in the boundary layer as compared to that of the potential flow. So we can write, if we, this is a conceptual thickness, so to say, but you can understand what it is. Rho uppercase U square delta double star, then it is it basically integration of u minus u infinity, that is the velocity deficit within the boundary layer, multiplied by the mass, that is rho into the local u. So u into rho into local u, that is lowercase u, uppercase u minus u infinity, this is the velocity deficit, this is the local velocity, and this is rho basically, and multiplied by area is the momentum. So rho u into flow area, that becomes the volume into rho mass, and this is the velocity. So this is the momentum u minus u infinity. So 0 to infinity rho lowercase u uppercase u minus lowercase u into dy. So delta double star, which is the momentum thickness, is finally given by, if we shift rho into u square on the right hand side, we can write delta double star equal to integration of u minus lowercase u by uppercase u multiplied by lowercase u by uppercase u dy, integrated between 0 and infinity. So this is the definition of momentum thickness. Now formally, we have to just talk something about laminar flow, although this difference between laminar flow and turbulent flow needs much more discussion. I will do that when we'll start turbulent flow. It is much more rigorous definition has to be given, but at the moment we can say that fluid motion, which is very well ordered, and as if one layer of fluid is sliding over another layer of fluid without getting undulated, that flow is called laminar flow. Again, I am saying this is not a complete definition. We will complement with many other attributes in course of time. Since it is introductory, I am just mentioning about it in that fashion, which is, as I said, well-ordered flow, as if fluid layers moving over another layer after layer, it is sliding over each other without getting undulated. That is the laminar flow. And turbulent flow is fluid motion, which is highly irregular, characterized by random fluctuations. And in the picture we have shown also. And for flow over a flat plate, usually when Reynolds number based on the plate length, distance from the leading edge, that is rho uppercase U into x by mu, and if at a critical distance, we will call it Reynolds number critical, and that critical distance is such that Reynolds number crosses a value of 5 into 10 to the power 5 for external flows over flat plate, or external flows in general also we can say. So, but on very convex bodies like circular cylinder, etc., these have to be again redefined. But usually flat flow and flow with mild curvature, we can say that this critical Reynolds number is 5 into 10 to the power 5, and Reynolds number is based on free stream velocity and distance from the leading edge x. So when it reaches 5 into 10 to the power 5, likely the transition from laminar flow to turbulent flow takes place. I will try to wrap up today's discussion with another very short topic. Usually we keep on saying that boundary layers are related to Prandtl number, and we have also said little earlier, that Prandtl number is of the order of delta by delta t. Delta is the velocity boundary layer thickness, delta t is the thermal boundary layer thickness. But what is the mechanistic viewpoint that we can relate the velocity boundary layer and temperature boundary layer with the Prandtl number? Now let us consider a case where flow is taking place over a heated plate, boundary layers have been formed, and this is delta T thermal boundary layer, and this is delta velocity boundary layer. And in this case, we have taken an example. We will take another example also. In this example, delta T is greater than delta. That means thermal boundary layer thickness is greater than velocity boundary layer thickness. We will consider, exactly the different case if it is otherwise also. But now let us consider a case when delta T is greater than delta. If it is so, then from the thermal boundary layer consideration, we can say within the thermal boundary layer, U del T del X is of the order of alpha del 2T del Y2. That means we have kept the highest convective contribution and highest diffusive contribution of thermal energy. U del T del X, highest term of the convective part, and alpha thermal diffusivity del 2T del Y2. If we again apply order of magnitude on this, and these are comparable within the thermal boundary layer. So we can say U infinity, this is delta T and this is L, proportional to alpha delta T by delta temperature divided by thermal boundary layer thickness square, delta T square. So from here we can write delta T by L square is proportional to alpha by U infinity into L. So this is very simple, just changing the sign. Delta T by L square is given by alpha. This delta T is boundary layer thickness and this del T is temperature difference. So this del T temperature difference across the boundary layer. So this del T gets cancelled out. We can write delta T by L square is proportional to alpha divided by U infinity by L. So we can write delta T by L square equal to basically alpha by U infinity into L. We just rearrange. We write mu divided by U infinity into L multiplied by alpha by nu. This new term, we insert here. We have a purpose for that, but we are bringing in such a way that nu gets cancelled out. This is basically molecular diffusivity or the kinematic viscosity. We are just bringing in, multiplying it by the kinematic viscosity, dividing it by the kinematic viscosity. So from the velocity boundary layer, again we can do same order of magnitude analysis within the boundary layer. We can say that highest convective term is of the order of highest diffusive term. So U del X is of the order of nu del 2U del Y2. Here again we can substitute highest representative term of U and X. So U infinity into U infinity by L is proportional to nu U infinity by delta square. So from here we can write delta by L square. This delta is velocity boundary layer thickness. Delta by L square is nu by U infinity into L. So delta T, thermal boundary layer thickness by L square, we get an expression. Hydrodynamic boundary layer or velocity boundary layer thickness by L square, we get this expression. So now if we equate these two, we can get a very interesting situation. We'll get delta T by L square equal to delta T by L square into alpha by nu. And from here we can easily write delta by delta T square, that means velocity boundary layer by thermal boundary layer square, is of the order of basically nu by alpha, and nu by alpha is Prandtl number. So we can clearly see here delta by delta T, if we bring delta T this side, so delta by delta T square, then it becomes of the order of nu by alpha. It is proportional to Prandtl number. So Prandtl number to the power half is order of or is proportional to delta by delta T. So when thermal boundary layer thickness is greater than velocity boundary layer thickness, then Prandtl number is related to delta by delta T in this way. That is, Prandtl number to the power half is proportional to delta by delta T. And this is a case where basically we can Prandtl number is less than 1, right? So the other case, that means when delta is greater than delta T, we have not discussed that. I am leaving it on to you. Having undergone this analysis that I have just done, try to find out how delta by delta t will be related to Prandtl number if delta is greater than delta t. If delta is less than delta t, then delta by delta t is proportional to Prandtl number to the power half. When delta t is greater than delta, Prandtl number to the power half is proportional to delta by delta t. Thermal boundary layer thickness is greater than velocity boundary layer thickness. But when it is other way around, velocity boundary layer thickness is greater than thermal boundary layer thickness, then the relationship is Prandtl number to the power 1/3 is proportional to delta by delta t for delta greater than delta t. But this I am not deriving. I have derived the other situation. This you have to attempt. Please attempt it and you will be able to derive it. We'll stop here today. Thank you very much. Thank you for very patient hearing. Thank you.